Introducing the Low-Cost Power Electronic Controller ECE Senior Design Project. The problem statement for our senior design project is as follows. The dSPACE controller used in the SB35 lab exceeds the functions necessitated by the laboratory parameters. This ultimately makes transportation, general maintenance, and relative cost a burden for off-campus use. The solution to this problem was to develop a low-cost portable testbed for off-campus outreach. The aforementioned dSPACE controller is a powerful testbed frequently used in EERC SB35. This testbed is used by ECE faculty member Trever Hassell for demonstrations outside of Michigan Tech campus. The image on the right shows a picture of one of the lab benches in SB35. Here you can see the detailed list of components present on the lab bench. In order to declare the project a success, our alternative testbed had to fulfill the following requirements. It must be able to generate 2 sets of 3-phase PWM signals, 6 in total. It must be able to interface or connect to the power electronic drive board or have an alternative means of powering the electric machines. The testbed alternative must also be Simulink compatible. It must be able to show that it can drive a permanent magnet DC motor, an AC induction motor, and a permanent magnet AC motor. It must also be capable of driving said motors in the ways described in the Machines and Drives lab procedures. Finally, this alternative testbed should cost no more than $400 per testbed. After conducting extensive research on different potential testbed alternatives, the team settled on 2 solutions, the BeagleBone Black and the TI Launchpad. Here you can see the original dSPACE control board along with the BeagleBone Black labeled option A and the TI Launchpad labeled option B. These controllers were developed simultaneously along parallel paths by splitting into subteams. The design path involved with the BeagleBone Black revolved around adapting the BeagleBone to the same role as the dSPACE controller. The BeagleBone Black was chosen for its fast processor speed, significant number of PWM and ADC I/O pins, and its similar usage as a controller in the mechanical engineering department. The BeagleBone would accept commands from Simulink that would control the analog output of the power electronic drive board, and in turn, the electric drive system. Although significant progress was made on the BeagleBone Black, it was ultimately abandoned in favor of its counterpart, the TI Launchpad. The TI Launchpad was identified as a unique design solution. Following the diagram on the right, it can be seen that the Launchpad replaces not only the dSPACE controller, but the power electronic drive board as well. This is achieved through the addition of 2 motor control boards, also known as boost packs. Here you can see a high-level diagram of the boost pack. Following the leftmost diagram, the boost pack has a set of I/O terminals. The one on the right represents input from a DC power supply. The leftmost terminals are for 3-phase output. Controlling the output phase voltage and current are the power MOSFETs. These FETs can be seen in the rightmost diagram. The TI Launchpad made its capabilities very apparent during the first phase of testing with a permanent magnet DC motor. The image on the right shows a high-level wiring diagram for DC operation. After a series of successful testing with the permanent magnet DC machines, focus moved to the AC electric machines, specifically an AC induction motor. The image on the right shows a high-level wiring diagram for the AC motor operation. Another obstacle that the TI Launchpad had to overcome was feedback from a quadrature encoder, seen on the right. This device is responsible for sending digital pulses that can be translated into measurements for speed and position. The pinout can be seen to the right. Ultimately, the TI Launchpad proved to be the most ideal project solution to the problem presented. Revisiting the project parameters, it can be seen that most of the project requirements were met within the timeline of this project. Thank you for listening to our video presentation.